Hello, everyone, and welcome to today's joint webinar on scanning microwave impedance microscopy. Our presenters for today are Sarah Ostrowski, Surface Property Manager at EAG Laboratories, and Ravi Chintala, Application Scientist at Prime Nano Inc. My name is Rena Samsu, Marketing at EAG Laboratories, a Eurofins company. Before we get started, I'd like to go over a few housekeeping items for today's event. All attendees have been muted. However, we'd still love to hear from you during today's presentation. You will have the opportunity to submit text questions to today's presenters by typing your questions into the questions panel located in the bottom right of your screen. You may send in your questions at any time during the presentation. Ian Mowat, Vice President of Materials Characterization at EAG, will be collecting these questions and moderating the Q&A session at the end of today's presentation. At the end of the webinar, a survey will pop up on your screen. Your feedback is greatly appreciated and will help us to improve our future events. I would now like to introduce our first presenter, Sarah Ostrowski, Surface Properties Manager at EAG Laboratories.
Thanks, Rena, and hi, everyone. Thanks for listening in on our Smart Chart webinar today. The topic is sMIM, which is an advanced electrical technique of AFM, or atomic force microscopy. EAG just added this capability a few months ago, and we are happy to co-host this webinar with our vendor, Prime Nano, in order to present this new technique to you. I'm Sarah Ostrowski, manager of the Surface Properties Group at EAG's lab in Sunnyvale, California. My group covers diverse techniques, including AFM, OP, XRF, TXRF, and nanomechanical testing. I'm excited that we have recently added Prime Nano's ScanWave Pro to our AFM system here in Sunnyvale, and I'm pleased to introduce you to the Prime Nano application scientist, Ravi Chintala, who will be presenting the majority of the technical content of today's webinar.
Thank you, Sarah. Hello, everyone. My name is Ravi Chintala. I'm an application scientist at Prime Nano. At Prime Nano, our team works on applications pertaining to semiconductor industry, specifically dealing with nanoscale dopant concentration. Prior to joining Prime Nano, I was a postdoctoral fellow at Lawrence Berkeley National Lab, and I obtained my PhD at KU Leuven IMEC in Belgium. Over to you, Sarah.
Thanks, Ravi. So today's webinar is going to be divided into three broad sections. First, Ravi and I will give introductions to our respective companies. Then Ravi and his colleague Nicholas will present the technical background for sMIM and show representative case studies. Finally, we'll wrap up with a Q&A session. Our goal for this webinar is to emphasize the usefulness of this technique by showing you data from real-world examples. To introduce you to my company, EAG, we are a global scientific services company with multiple locations worldwide, such as in the US, Europe, and Asia. And we are part of the bigger Eurofins family. We have over 600 highly educated and experienced employees solving customer problems with a diverse suite of techniques located in 20 different sites. We serve over 4,000 clients in 50 countries. Currently, sMIM is only available here in Sunnyvale, but we do have AFM capabilities in the Netherlands. Next, let's take a look at the SMART chart, which is the inspiration behind the seminar series. This chart highlights the techniques we have available at EAG, and they're plotted to show their attributes related to spot size and detection limits. Each of the bubbles represents a different analysis technique, and the bubble size indicates detection range and analytical spot size. The x-axis shows the range of spot sizes from 1 centimeter down to 1 angstrom. The y-axis shows concentrations either in atoms per cubic centimeter or atomic concentration. The bubbles are color-coded according to the descriptions at the lower left. So for example, the dark blue colors indicate that technique provides elemental information, and green bubbles indicate that technique provides imaging information, such as AFM. sMIM is colored a deep maroon because it provides information on electrically active dopants. The placement of the bubbles is also meaningful. The surface chemical analysis techniques are inside of the box. Outside the box on the right are bulk techniques, which have a range of detection limits, but they don't provide information regarding depth. And the box below the box are the imaging techniques, which can measure surface properties and features of various sizes, but don't inherently provide chemical composition information. Another important measurement parameter not covered in the bubble chart is analysis depth. The distance that a technique measures into a sample may help dictate whether a technique is appropriate for a given application. So you see sMIM can actually detect subsurface signals down to a few hundreds of nanometers. And finally, before we delve into the technical details of sMIM, it might be useful to have a quick refresher on how AFM itself works. The most basic mode for AFM is known as contact mode. This mode is also the basis for many of the electrical techniques like sMIM. The schematic on this slide shows the main components and configuration for our Bruker dimension icon AFM instruments. A probe, which consists of a springboard cantilever and a fine radius tip, is attached to a piezoelectric tube scanner. The PZT scanner allows precise control of the probe movement. Also, there's a laser and a position-sensitive photodiode and feedback electronics. So in contact mode, the tip is raster scanned in direct contact with the surface, while a laser light is pointed or is reflected off the backside of the cantilever onto the photodiode detector. When the tip crosses a point at a new height, the position of the light on the detector changes too. The feedback electronics then maintain a constant position on the detector by adjusting the cantilever height with a bias applied to the PZT tube. The voltage is converted to height in the instrument software. So contact mode AFM is one of the modes that's used for the sMIM technique, which Nicholas and Ravi will cover after a brief introduction to their company. I will now hand things over to Nicholas.
Hello, and thank you for attending today's webinar. I'm Nicholas Antonio, and I will give you an overview of Prime Nano and then hand it over to Ravi, who will cover our technology and present results from multiple case studies. Prime Nano was formed by two Stanford University professors, Z.X. Shen and Mike Kelly. Prime Nano has exclusive rights to multiple patents in the field of scanning microwave impedance microscopy. Our first product was introduced in 2013-2014 and was the ScanWave 1.0. It's been used in imaging of electrical properties of materials at the nanoscale. Over the last several years, we have invested heavily in R&D and recently brought to market the ScanWave Pro with over 10x improvement in performance over previous and competing products. We make our own probes in a patented process, and they will be described later on. Today's webinar will focus on the ScanWave Pro technology and case studies. This system is available at EAG in Sunnyvale, California. So a little introduction of the technology. Scanning microwave impedance uses microwaves that are emitted from an AFM tip, and the reflection is analyzed to provide information about the permittivity and conductivity of material at the nanoscale. We use patented shielded probes to deliver the microwaves to the tip and collect the reflected signal. Because we use microwaves, they can penetrate up to a few hundred nanometers deep, so we can image buried features. And this is compatible with a large variety of materials, and we'll cover some of them in our case studies here. So now I'd like to go over the technology, performance, and benefits. ScanWave Pro is a breakthrough product that improved the state-of-the-art of the technology with regard to sensitivity and spatial resolution. First of all, I'd like to point out that we have achieved unparalleled sensitivity at sub 0.1 attofarad for capacitance. Combined with unmatched signal-to-noise ratio, our systems reach spatial resolution in the sub-10 nanometer range. The high power capability enables subsurface imaging to a depth of more than 200 nanometers. Because we use microwaves, there's no need for an electrical contact to the sample, and we can also image insulating material. This greatly simplifies sample prep and setup. All common AFM modes are supported: tapping, contact, and non-contact, etc. In addition, we provide 6 channels of information, so you can overlay topography information to electrical properties, and this is very powerful. Our probe exchange has been streamlined. You don't need any special tools. It's a very simple process. I'd like to reintroduce Ravi now, who will go into more detail about our products and the applications.
Thank you, Nicholas. I would like to start with the working principle of scan wave systems and sMIM technique. Here we see the schematic of the sMIM setup. We have the scan wave electronics from Prime Nano, to which we send 3 GHz microwave signal to the sample through a probe, and the probe is completely shielded to avoid any background capacitances. The microwaves create a near-field electromagnetic field at the tip apex, interact with the sample beneath. The reflected signals from the sample surface, which contain the electrical information about the sample, are sent to the scan wave electronics. The scan wave electronics process the signal and output the impedance of the sample. Now, the impedance can be converted into capacitance, which is the imaginary component of the impedance, and the resistance, which is the real component of the impedance. So we can essentially get capacitance and resistance when you image using the microwave impedance. As the probe scans over the surface, you get the relative variations in the capacitance and the resistance. For a semiconducting material system, which is a non-linear system where the capacitance can change with respect to applied voltage, if you apply another voltage like an AC voltage or a DC voltage between the tip and the sample, you can plot a DC-dV or variation in the capacitance with respect to voltage. From a lock-in output, you get the phase and amplitude signals. Phase represents the polarity of the charge carrier, whether it's a p-type or an n-type, and the amplitude represents the magnitude of the charge carriers. Here is shown an image, an example where the scan wave electronics is connected to the Bruker icon. Our Prime Nano scan wave electronics is connected to the AFM head through a coaxial cable. This is where the microwave signals are sent. The probe interface module, and a picture of it is shown here, indicates where the probe is connected and sends the microwave signals to the sample. As you can see, the probe interface module is a simple tool wherein you can change the probe interface module and load the probes with just a thumb screw. So this is to make the process of changing the probes easier for the user. We also have the power supply unit, which is one of the lowest noise power supply unit, which is important to obtain high sensitivity and a very good spatial resolution as well. Now, on the right, we have some scanning electron microscope images of the probes that are being used. You can see a very sharp apex of the tip at the tip apex. At the bottom, we have the schematic of the probe, which shows that the cantilever itself is completely shielded. Only the pyramid of the probe is exposed. When you shield the cantilever completely, this would reduce the microwave source only to be from the pyramid, and that increases the sensitivity of the measurements. Further, this helps in getting high spatial resolution, which is sub 10 nanometers, and I'll show you a few examples in the next slides where we obtain this kind of spatial resolution. As Nicholas mentioned earlier, apart from the topography channel, which is by default when you're looking at an atomic force microscope, you can get localized variations in the permittivity, conductivity, and you can also use either DC-DV channel or a DR-DV channel to get information about change in capacitance or the resistance of the sample that you're looking at. To reiterate the performance of the ScanWave Pro system, the sensitivity with respect to capacitance is less than 0.1 autofarad. With a spatial resolution of less than 10 nanometers. This is very important when you're looking at nanoscale variations or devices at nanometer scale node. As we are looking at microwaves in the near field regime, these microwaves penetrate deeper into the surface, and you can also get information from the depth of the sample, or subsurface imaging is possible with microwave impedance microscopy. This is one of the unique properties, and it's not easily obtained using any other AFM techniques. As we have a probe which is full metal probe, there is no problem with tip wear. You can easily get the tip back or resolution back even if the tip contaminates or breaks. As we're dealing with RF waves or microwaves, there is no need of electrical contact. This actually helps in simplifying the sample preparation and also the measurement setup. For a device which is in the nanometer node, you need to have a back contact very close to the measuring device, which is not required for microwave measurements. We have a streamlined probe exchange, which is very similar to other electrical AFM techniques. So this is a huge advantage. And there is a less training required for a user to get used to microwave measurements. The response of the microwave is log linear with respect to variations in the permittivity or the dopant concentration. I'll come back to this property in the next slide. From the measurement capabilities point of view, you can get multiple channels. You can get capacitance, resistance, and DC-DV and DR-DV channels. And from the atomic force microscopy measurement technique point of view, this sMIM is suitable not just in contact mode, but you can also use other AFM modes such as tapping or peak force mode, which are suitable for softer material systems. Here we see a graph which shows the sMIM response with respect to variation in the dielectric constant on the x-axis. The x-axis is a logarithmic scale and the y-axis is a linear scale. As you can see, as you vary the dielectric constant for about 3 orders of magnitude from around single digits to about double digits, you can clearly see that the response of the sMIM is linear and it is monotonous, that it is increasing in only one direction. This is helpful, especially when you're dealing with thin film dielectric materials and you want to quantify or know a dielectric constant of an unknown material system. On the right, we have the similar graph, but the variation is monitored with respect to the dopant concentration. The usual industry standard dopant concentration is in between E15 to E20. That is exactly what we are tabulating here. And the graph shows a linear response of the sMIM with respect to variation in the dopant concentration. Here we show in depth of what exactly we mean by that. This is a standard sample of a substrate which has a P substrate which has 10 implants of P and 10 implants of N, with the dopant concentration varying from 5E15 to about E20. As you can see, the sMIM response is very linear, both for the N-type and a P-type, and this will serve as a very good reference sample. On the bottom, you see the typical CV response of the sMIM for P-type and N-type, which are mirror images in respect to CV response. But you also see variation in the CV response with respect to the variation in the dopant concentration. So ScanWave systems can clearly distinguish dopant concentrations between E15 to E20 and can also identify between N and P type material systems. In the next slide, I want to show a real life example of an insulated gate bipolar transistor here. On the top, we have the scanning electron microscope image of a cross section of the device. And you can clearly see there are some voids in these trenches. The other similar electrical AFM technique called scanning capacitance microscope cannot distinguish these trench gates, voids in the trench gates, but sMIM capacitance image, which is shown on the right here, clearly can distinguish these trench gates, the voids in the trench gates. Apart from that, we can also look at the gate oxide and also the emitter region, which is a semiconductor region. So as we are looking at only capacitance signal, which can come from an insulating or a semiconductor sample, you can look at insulating, semiconducting, and also metallic regions all at once in scan wave measurements. Now, as I've mentioned, that the spatial resolution that can be obtained with the scan wave systems is less than 10 nanometers. And I want to show you one example wherein we have the 7 nanometer node FinFETs. On the top, we have the representative scanning electron microscope image, and then you have the topography of the cross section, and you can look at the topography is very smooth. It doesn't indicate the presence of any fins at all. And if you look at the sMIM response, and I want to zoom in a particular region wherein you can see these fins, and I take a line cross section across these fins, you can clearly see a full width half maximum of about 10 nanometers in this. Further, this device, just to be protecting, has a protective oxide layer, which is about 3 to 4 nanometers. So the microwaves penetrate through this oxide layer and be able to look at the contrast between the silicon and the field oxide, which is deposited in between the fins, and still get a spatial resolution which is less than 10 nanometers. In the next slide, I want to show you another standard device, which is a memory device. It's an SRAM device, and this has been deprocessed to the active layer. And at the bottom, you see the height sensor. This is the topography information, and then sMIM capacitance signal, DC/dV phase and amplitude signals. And the capacitance signal can identify variation in the dopant concentration, and you can clearly see the DC/dV phase signal, which identifies the P regions and the N regions separately. On the top, we have a merged topography and scan wave image signal, where you can clearly identify the lightly doped drain regions, which are N, a P region, which is in blue, and also the N channel, which is in the yellowish region. So all of this, you can look at the polarity of the dopant and also the magnitude of the variations in the dopant concentration. As I've mentioned, microwave signals can penetrate deeper into the surface. We wanted to look at a device without actually deprocessing it completely. So here is a non-volatile memory cell. It's an FPGA cell which has some stored charges and has been deprocessed, but it still has about 100 nanometers of silicon from the backside, and we are looking at through the sMIM, looking at the stored charges. And you can clearly see the difference between the charged and the not charged regions. This is a very good example of actually, in a way, spying a device without actually completely opening it up. While the charges can be clearly seen here, this is a large device. This is only for demonstrative purposes. And we wanted to check how deep that the microwaves can penetrate to. And for this, we made our own structure. Here we have a cross-section of the device wherein we have a silicon substrate. On top of it, we deposit silicon oxide islands. This is about 90 nanometers thick. And over that, we deposit silicon nitride. and completely polish it so that there is no topography. As you can see from the image here, there is no topography, that you cannot identify anything from the topography image itself. But when you look at the sMIM capacitance image, you can clearly see the difference in the capacitance between just the silicon nitride or a combination of silicon nitride and silicon oxide. And mind you, this is about 200 nanometers deep into the surface. And if I take a line cross section, again, this is a single line cross section, so you don't need to average at all. And you can clearly see hundreds of millivolts of variation between the capacitance contrast. And this helps in identifying buried structures as well, especially when you have a device which might be degrading when it is exposed to air atmosphere. These microwave imaging is extremely helpful. And to showcase this case, we have a small video and to show how easy it is to image. I'll try to click this thing. For some reason, I cannot play the channel. Okay, it plays now. What we see here is a frequency sweep wherein we sweep the microwave frequencies and only one frequency is selected, which is about 3 gigahertz. And I fastened up the video just to show the topography on the top left here. And then we have the sMIM image, capacitance image showing in the bottom left here. We can clearly see that while there is no variation in the topography, there we can clearly see the islands which are buried deeper. It's about 200 nanometers deeper into the surface. Now, as I've mentioned, this kind of technique is useful for softer materials as well. To look into these softer materials, we have looked into carbon nanotubes. When you have carbon nanotubes on a substrate, and if you're scanning in contact mode, these nanotubes will be dragged along with the tip. So to avoid that, you use other techniques such as tapping mode, where you intermittently contact the sample. Now, these carbon nanotubes are on a glass substrate. That means these are on insulating material, but because we do not need any back contact with the microwave measurement, this is you can see these carbon nanotubes even without any electrical back contact. On the left, we have the surface AFM image of topography, but we cannot clearly distinguish these nanotubes because we are still hovering above this water layer or the moisture which is present on the surface. On the center image, you have the sMIM capacitive image. You can clearly distinguish individual carbon nanotubes. And if I zoom it up in further, you can see how these wires or nanotubes bend very well. And you can find them a sharp transition between the glass and the carbon nanotubes. So the bottom line of this is that sMIM or ScanWave is using ScanWave, you can use it in tapping mode as well. To break the water layer and probe the nanotube itself, we use peak force mode, wherein the topography shows the nanotubes. Here we have 3 single nanotubes. These are multi-wall nanotubes. And if I take a line cross section across this sMIM capacitance image, I can clearly distinguish the background glass substrate and also the nanotube with a very high signal to noise ratio. And if I take a look at the variation here, this is about 8 nanometers. Here I'm including even the tip convolution. While the nanotube could be about 2 to 3 nanometers, including the tip convolution, you get about 8 nanometers variation. This means that we can get sub 10 nanometers resolution on or using ScanWave systems with a very high degree of sensitivity. To push our resolution and the proof of concept that we can actually image even higher spatial resolution, we look at the 2D material systems. Here, when you have 2 regular patterns of monolayer atomic thick materials superimposed on each other, a new pattern emerges called moire pattern or fringe pattern. As you can see on the image on the left, you see this periodicity of this moire structure or the fringe structure. And the periodicity varies, depends upon the twist angle between the individual layers as well. On the top here, we have the optical image wherein we have the silicon oxide substrate, and we are looking at the hexagonal boron nitride, which is an insulating material, and monolayer graphene deposited on the flake of the hexagonal boron nitride. Usually to image these material, you need very high vacuum conditions or ultra vacuum conditions using scanning tunneling microscope. But with sMIM, you can do it in room temperature and air ambience pressure. And you can see the from the sMIM-C image, you can clearly see the honeycomb structure of the moire superlattice. And if I take a line cross section across this, the periodicity gives me about 14 nanometers. And a full width half maximum of the variation gives me about a spatial resolution of about 4 nanometers. And as I've mentioned earlier, that we can change the moire superlattice periodicity by changing the twist angle. We look at another sample. Instead of a single crystalline graphene, we look at the polycrystalline graphene. And if you look at the topography, you do not see any variations. It is actually close to the noise level of the system in the contact mode, less than a nanometer variation. And if you look at the capacitance image, you can clearly see the boundaries between individual crystalline structures between the graphene and hexagonal boron nitride. And you also see some regions wherein the periodicity of the moire structure can be seen. Upon closer inspection, we can not just see one periodicity, but two periodicities, in this case about 14 nanometers and also 5.5 nanometer periodicity. And I zoom in this particular region. This is about a 50 by 50 nanometer square scan size. And you can, taking a line cross section for this, can clearly see the 5.5 nanometer periodicity. Not just that, but you can also see these defects which are present in between these two layers. This is about 1 to 2 nanometers in diameter. So using ScanWave Pro, you can clearly see even 1 to 2 nanometer spatial resolution with a very high degree of sensitivity in the signal contrast. One of the last applications I want to discuss is the ferroelectric sample. This is in rare earth element. The schematic of the sample is shown on the right here, top right, wherein it has two different phases of the orientation of the domains. One is top and the other is down, indicated in the green and the blue signals here. Not just that, but it also has three different phases where they unite or come together at one point. If you look at the topography, it still has a lot of contamination on the surface, but when you look at the capacitance signal, you can clearly see the difference between individual phases or individual polarity, up and down polarity. There is a variation in the capacitance. Now, if you look at this sMIM-R channel, which is the resistance channel, you can see that the domain walls conduct or brighten up much more compared to the domains itself. Even that the vertices where the domains contact are blown up much more. That means they are even more conducting than the domain walls itself. Now imagine this is a very insulating substrate, which is a bulk sample of about hundreds of micrometers, can image electrical properties without actually having any back contact or any contact or electrical path for the channels to go. So this is one huge advantage of the ScanWave systems. To summarize, I hope I've convinced you that using sMIM, we can measure local variations in the permittivity and conductivity, and also measure carrier type and carrier concentration for semiconducting materials. As essentially we are measuring the permittivity of the materials, this technique is compatible with a wide range of material systems. You can look at dielectric materials, insulators, semiconductors, all the emerging material systems such as 1D materials or carbon nanotubes, or 2D materials such as graphene. You can look through the insulating materials such as ferroelectric and magnetic materials. And this is compatible with various AFM measurement modes. You can do it in contact mode, you can do it in tapping or peak force, other techniques as well. This can be operated at room temperature as well as low temperature. You can apply it high vacuum conditions, and you can put in high magnetic fields as well. Again, from the capabilities point of view, you can do point spectroscopy, the CV curves, or you can apply an AC or a DC bias to understand the device much better. You're not just going to measure surface, but also subsurface information, which is a unique property from an electrical AFM technique. With this, I would like to thank you for your attention, and I would like to hand it over to Sarah.
Well, thank you very much, Ravi and Nicholas, for a wonderful webinar on sMIM. Before we conclude today, I wanted to briefly mention that there are several other techniques that are complementary to sMIM. Two of these include other AFM-based approaches, such as scanning capacitance microscopy and scanning spreading resistance microscopy, and we covered these in an earlier webinar. Non-AFM techniques for characterizing dopants include DHEM, differential Hall effect metrology, and dynamic SIMS. You can access recordings of the webinars covering some of these techniques on our website. And I believe Rena is also going to add a link in the chat window. So why choose EAG? There are several reasons, but I think that one important attribute is we take client confidentiality very seriously, and we even do regular business with export control and ITAR companies. EAG has been around for 40 years, so we have very experienced experts and streamlined processes in place to make your project go smoothly. Many of our techniques are ISO 17025 accredited. We are a global leader for materials testing services with a broad range of instruments and expertise, and that leaves us poised to take on the most challenging materials and engineering-related issues. Finally, in light of the pandemic that's affecting all of us, I want to emphasize that EAG is committed to the safety of our staff and clients. Worldwide, we have complied with the latest COVID regulations from state and local governments, as well as the CDC. Currently, all of our locations are open, but we may have limitations on customer visits. Since this is a fluid situation, if we are operating a lab at a reduced capacity, we may be able to transfer your samples to another EAG location. And we encourage you to discuss your options with our sales reps.